Okay, so today we're going to talk about titrations, what they are, why we use them, and how we can interpret the results. So let's go ahead and jump in to our PowerPoint here. Maybe. There we go. Okay, so we're talking about titrations and specifically about titration curves. So what is a titration? First of all, a titration is just the controlled addition of an amount of a solution of a well-known concentration that is required to completely react with a measured amount of our solution of unknown concentration. The purpose of a titration is to use the volume and concentration of a known solution in order to determine the concentration of an unknown solution. This can be done with an indicator, or it can be done potentiometrically, meaning a measurement of the pH as we go through the titration, as is shown in this image. But the purpose of a titration is to determine the concentration of a solution of unknown concentration. So we can either use, as I said, a pH meter or an indicator. And so you can see in this image that we're using an indicator, so it has changed color. And the purpose of either an indicator or a potentiometric titration is to identify what we call the equivalence point. So the equivalence point is the point at which stoichiometrically equivalent amounts of acid and base have been combined. So the two solutions used are present in chemically equivalent amounts. It's important that you guys recognize that this is not necessarily neutral. As we talked about in class, if we have a weak acid and a strong base, or a weak base and a strong acid as our titration, the titration is not necessarily going to reach equivalence at neutrality. And so what we're looking for is those stoichiometrically equivalent amounts. So that's what we call the equivalence point. There's also a term that sometimes gets used interchangeably, which is called the end point. And the end point is the point in a titration at which the indicator changes color. So we're going to talk about how we choose our indicator so that it changes color as close to the equivalence point as possible. So when we titrate a strong acid with a strong base, from the start of the titration, at the beginning of the titration, you can see we have just hydrogen ions or hydronium ions and chloride ions floating around in our solution, and we have a lot of it. And so as we're adding base, the pH is going to go up slowly. But when we get close to the equivalence point and just after it, the pH is going to change rapidly. And so now we have a tiny bit of remaining acid beforehand, but again, not the acid itself, but the hydronium ion and the chloride ion. At this point, at the equivalence point, we should have no hydronium ion left, no hydroxide ion left, just water and sodium ions and chloride ions. At this point, the pH is going to change very, very rapidly to the point that 1/10 of a milliliter is going to cause a significant change. So at the equivalence point, the moles of acid is going to be equal to the moles of base. We're going to have only water and salt, meaning sodium ions and chloride ions. So here we were just before, we still had a few hydrogen ions left. Now we have just hydrogen ion, sodium ions and chloride ions and water. As we move past the equivalence point, now we're going to start to see hydroxide ions. We still are going to have sodium ions and chloride ions, but the concentration of sodium ions is going to start to exceed the concentration of chloride ions, and we're going to start to have hydroxide ions, and that's what's going to control the pH of the solution, so the pH is going to level out. At this point, the pH of the solution is determined only by the concentration of the excess strong base. So we can use stoichiometry to calculate the pH here. On the other hand, if we titrate a weak acid with a strong base, as we move through the titration, at the beginning, we're mostly going to have undissociated acid and a very small amount of hydrogen ions and conjugate base. But as we add the hydroxide ions, as we add that strong base, it's going to start to react with the acid, undissociated acid, which is then going to free up some of those conjugate base ions, in this case, the acetate ions. And so we're actually going to start creating a buffer mixture where we're going to have both undissociated acid and conjugate base. And so the pH through this section is being controlled by the equilibrium reaction between the conjugate base and water and acid and water. So slow change through this area, and we have a mixture of undissociated acid and conjugate base ions. At the equivalence point, we should have only sodium ions and the conjugate base ions, which again, in this case, is the acetate ions. So the equivalent pH at the equivalence point, instead of being neutral, is going to be governed by the reaction of the conjugate base with water. And so it's going to be basic. It's going to be slightly above 7. And once we get past the equivalence point, again, we're adding excess strong base. And so now the pH is going to be controlled by the quantity of strong base. So now we're back to a stoichiometry problem. But right at the equivalence point, it's an equilibrium situation. In these kinds of titrations, because the equivalence point is above 7, it's usually around 8 to 8.5, phenolphthalein is a very common indicator. So at every point below equivalence point, the pH is determined by the amounts of the acid and the conjugate base present at that particular time. And so we can use an equation called the Henderson-Hasselbalch equation, and we'll talk about that equation more when we talk about buffers. Once we reach the equivalence point, we're going to use the equilibrium calculation to determine pH. And when we add excess base, then we would use the concentration of the excess base to determine pH. So we have lots of different ways to calculate pH depending on where we are in the titration. So weak acids are going to start out at a higher pH because they don't dissociate completely. And the pH changes near the equivalence point are going to be more subtle. They're going to be harder to see. And so very often with weak acids, you have to use a derivative of the curve in order to actually determine for certain what the equivalence point was. If we have a polyprotic acid, meaning an acid with more than one hydrogen ion, more than one removable hydrogen ion, there's going to be an equivalence point for each dissociation. So here we have phosphoric acid, and you can see that we have a clearly defined equivalence point for when the first hydrogen ion is pulled off of the hydrogen phosphate, or the phosphoric acid molecule. This is stepwise because this is governed by the equilibrium. And so rather than some molecules being more dissociated and some molecules being only singly dissociated, it really is going to be a reaction where the single dissociation is going to happen first and then the subsequent dissociation. So we can see that we have two different equivalence points. By the time we reach the third equivalence point for phosphoric acid, it actually is exceptionally difficult to see because the reaction is really governed by the hydroxide ion at that point. So it's really very difficult to determine that third dissociation point. But polyprotic acids are going to have multiple dissociation points. Okay, so if we look at graphs of strong acid, strong base titrations, we know that the endpoint and the equivalence point are both going to be at a pH of 7. And so what we see here is a solution of 10th molar hydrochloric acid being titrated with 10th molar sodium hydroxide. And we can see that it took 20 milliliters to reach the end point. And so we would be able to calculate the concentration of the hydrochloric acid if we didn't know it. This one, we've already been told that it's 10th molar. If we were to perform the same titration on acetic acid and with sodium hydroxide, you can see that the endpoint is above 7. You can also see that there's a much more gradual slope in the pH change. There's more of a slope to the pH change prior to the endpoint. We don't always titrate with base. We sometimes titrate base with acid. And so that's going to result in starting out at a high pH and ending at a low pH. But again, because this is strong acid, strong base, you can see that we have a very, very steep change at the equivalence point, and that the endpoint is at 7. If we titrate a strong acid with a weak base, we have an endpoint below 7 because the equivalence point, the pH at the equivalence point, is dominated by the equilibrium reaction of the acidic salt. So because we have different equivalence points, we have to choose indicators for the particular titration system. And we need to choose that indicator based on the pH at the equivalence point. So we would need to do some calculations ahead of time in order to determine what the pH at the equivalence point is going to be. And then we would look at a chart like this one that would tell us where the indicator changes color. And so if we had something that changed that had an endpoint near 5, we could use methyl red because it changes there. We could also use brome cresol green, but it would be more difficult to see. We could use, if we have one that changes pH near 6, we could use alizarin or brome cresol purple. Both of those would be good indicators. These acid-base indicators are just Bronsted-Lowry compounds. They have different colors in their acid and base form. So as an example, phenolphthalein in its acid form is colorless, but in its basic form turns pink. And so it's used as an indicator because it changes color as the pH changes. The pH at which that indicator changes is dependent on the Ka of the indicator as a weak acid. So we can use that to determine what the appropriate indicator would be. As an example, when we titrate a weak base with a strong acid, the equivalence point is going to be below 7. So we would probably choose something like methyl red that would change color in that time zone. Okay, the one other tool that we use titrations for is to determine Ka. So if we have a weak acid or a weak base, in this case we have a weak base, the color change the pH halfway to the equivalence point is the pKa of the acid. So if we want to determine the pKa of an acid, we can titrate it and we can determine the pH at the half equivalence point, and we can use that to find the pKa of the acid. So I hope that's helpful. If you have questions, let me know.